All right. So welcome back, everyone. So this is so the second lecture on linear algebra review. So me trying to cover all of linear algebra in like 3 lectures, and trying to make kind of linear algebra exciting for 3 lectures. So lots of review. If you've had linear algebra before, hopefully the perspective is maybe a little bit different, and it's so going pretty quickly. So we'll be doing this. Yeah, let's see. We've done the first one where we just reviewed addition and multiplication. We're going to talk about norms and linear independence. These are, again, kind of very important properties which will really describe the basis of, or the basis. So now, pun intended, now that I see that, for understanding doing linear regression in higher dimensions, doing dimensionality reduction in higher dimensions, and actually everything in class, right? We'll describe all the algorithms in terms of linear algebra, so you need to be comfortable with these terms. Hopefully you should have had before, so this should be easy, should be reviewed, but these notation is like going to be super important. So you have to be comfortable with this. Let's see, we're going to do an example, go through this in NumPy and Python at the end of the lecture today. Okay, it's pretty straightforward to do it. The 4th question on your homework, the homework 2 is due in a week. Okay, the 4th question is meant for you to do in Python. It's not meant to be hard. You could do it by hand or something else, but I'm trying to force you to practice using Python, and after seeing kind of the example today, it should be kind of pretty easy to do. Okay, that's the point, but to force you to kind of get used to it. We'll be doing more advanced things with Python the next couple of homeworks, so you're going to want to kind of practice it now. Good. Okay, what else? Quiz number 2 is going to be on Thursday. Okay, quiz 2 will cover this topics on convergence, central limit theorem, these concentration and measure bounds, and then linear algebra. I'll keep it, I think we'll pretty much keep it to the lectures on last Thursday and today. We'll do a little bit more linear algebra on Thursday before the quiz, but I think the topics will be confined to this. Again, sometimes linear algebra, it encodes a lot of stuff, so you can write it down in a way which is pretty simple, and then encodes a lot of computation in it, right? Multiplying 2 matrices together is a lot of multiplications and additions of individual scalars. I will not ask you to do a whole bunch of calculations on the quiz. That's not going to be so feasible, but you are going to need to know the basics of those things, right? The quizzes are not meant to be especially challenging. They're meant to be a review for you of the material you've seen over the past couple of weeks. Okay. Last time, I think on quiz 1, the average score is about 91. Okay, that's what I'm about aiming for, right? That seems reasonable. Occasionally, you make a silly mistake on these things. Over the course of the 6 core quizzes over the semester, those should hopefully average out, but try and be careful on them. Again, you can get 5 points back by having a cheat sheet that you turn in, have it preloaded on your device so that you can upload it easily. The idea of that is that, the idea of the quiz is that you are kind of reviewing the material just a little bit every week after class. Maybe go back and figure out what you think was the quarter of a page worth of material that was most important and recorded on a cheat sheet. This is just a way for you to keep reviewing stuff, so you're not just sitting in lecture, but you go and try and do something with it, okay? That's the mechanism, the goal of these quizzes. Okay. All right. One other thing we talked about was the office hours. Okay, and yeah, so people were saying, oh, there aren't as many office hours on Thursdays and in the later half of the week. Reminder, I have office hours on Zoom on Friday mornings, and then I've set aside time after every class, including on Thursdays and today's. So that is on some Thursdays and Fridays, but there weren't the TA office hours. I posted a survey quiz on Canvas, and the results were not too conclusive on this quiz. About a quarter of you responded to the quiz, and of those, there was a slight preference for moving Hao Cheng's office hours to on Thursday afternoon, but it was not that dominant. A lot of people wanted them to stay. His current time was also one of the most popular times people could actually make. Okay, so what I think we're going to try and do, and we're still working out the details, is we're going to try and have at least one TA office hour on Thursdays or possibly Fridays each week, in addition to the current ones. But it will be kind of distributed among the TAs, and we'll try and announce it on Canvas every week. It will be put in this Google calendar that encodes all of the class times and the office hours and the Zoom links and everything. So you can always find it on there. You're welcome to follow this calendar. And for example, this week, we've added one office hour on Thursday. So Manoj is going to get one from 1:30 to 2:30. Okay, in addition to my office hour. Okay, so I think he'll announce that on Canvas. We'll try and do this each week. We're not going to, there are like 9 weeks, regular weeks left of this semester. So there are 4 TAs, they'll do 2 each. And so we're not going to do one next week, but we will do one the following week. So Peter will do one in the morning here. Okay, the reason for that is the third homework. Okay, I think this is mostly about the homework. So third homework, because of fall break, it's not due until October 26th. Okay, and so I might not have it posted by next week, Thursday. Hopefully it will be posted by then, but it might not even be posted then. So this is a small gap you'll actually might be in between homework. So we're not going to do one next week on Thursday, but we will have one on this week for those who want to get started, and Thursday is a good time. Homeworks 3 and 4 will be ones that are a bit longer. There'll be an implementation sort of thing you'll do that'll be a bit more involved than you will the other homeworks. So those you want maybe spend a little bit more time and effort on those. Okay, so this seems like an okay plan. Hopefully a compromise of the goals. And those Thursday ones will I think will probably be on Zoom for those of you. I guess people were pretty happy with the amount of in-person office hours, but preferred a little bit more Zoom ones. So those ones will probably be all on Zoom as well. And if there is need, if you're not getting, if the office hours are too full, you're not getting kind of able to talk to the TA or myself in the time, let me know, and we can reassess the situation on the fly as well. And and if you ever need to see me outside the times, feel free to make an appointment with me as well. Okay, great. So I think that's about it. We're working on grading homework 1. Hopefully this will be done kind of, I expect some point this week. All right. Okay, linear algebra review number 2. All right, so we reviewed last time that that we have vectors, and I'll try and use a V or a lowercase letter, and this will say an element in RD. This would be kind of V equals, say, V1, V2 up to VD. And so matrices, let's say this is A, and this would be an element of R, say, N plus D. That means it has N rows and D columns. So we'll think of a matrix, say A11 up to A12, all the way down to AND. This would be A21. Okay, and it's kind of this two-dimensional array, right? Or you can store it as an array of arrays, where every row is a vector and so forth. We talked about adding and multiplying these on last week on Thursday. One thing we talked about was the dot product, right? Well, let's just draw this setup here again. And we talked about, let's see, if we have a vector u and we have another vector v, and in particular we look at the line which goes through u. Okay, so under the condition that the length of u is equal to 1, then the dot product of u and v, I can understand this by thinking of this point. This is the projection onto u of v, and if this is true, then the dot product of u and v, which is a certain type of multiplication, was going to be the length of the projection of u of v onto u. Okay, so the length here that measured this length from the origin. I can think of this now as this vector from the origin. I've offset it a little bit so you can't see, but it actually goes right through u. Right, the length of this vector is equal to this dot product as long as the length of u is 1. Okay, and I said that, okay, we could write this length of u equals 1 equals this. There's this notation here, and I didn't explain that. Okay, the first thing we're going to talk about today is how to talk about this length, and these are called norms. Okay, so this is a norm of u. Okay, the norm of u is 1. That means the length is 1. Then this nice property about the dot product holds. And then again, the result of the dot product is the length of this vector projected on. Okay. Okay, so norms. Okay, so let's start with norms of vectors. Let's define this norm of vector v in RD. I'm going to write this as this 2 parallel vertical lines. In LaTeX, you can all do like a slash bar. So this is a slash, and this is a bar, and then we'll draw these, and I'll say it's a little bit closer than if you did 2 of these vertical lines. This is something that's actually on your keyboard. So on there someplace, so you can draw that. Okay, so this is defined, and this measures kind of the straight line distance, right? This picture back over here where I measure the distance of this, right? I say this distance is 1. I really mean if I have a piece of string and I put one end of the string on one end of the vector, one end on the other end, how long is that string? It's that straight line distance that I'm measuring here. Then I can formalize this as Euclidean distance. Okay, this is the Euclidean distance, and this is written as, so I write all the coordinates, I square all the coordinates, I add them up, and I take the square root. Okay, this is the straight line distance. You're probably familiar with so Pythagorean theorem, right? I can do, so let me, maybe that picture is jumping ahead a little bit. Let's draw this way. Let's say this is the 0 vector. This is V, and I can think of the V is actually in 2D is V1, V2. Okay, so the V1 distance, this is V1, this is V2, right? So the V2 coordinate, this is the origin. All right, the V1 coordinate is this length, the V2 coordinate is this length. Okay, and I want to get the length of this vector here, right? So let's call this term, this is the length of the vector, right? This length here, this is the hypotenuse. So I know that this squared is equal to V1 squared. V1 is just a scalar value, right? So I don't need to put the norms on it. It's just a value. That's one coordinate plus V2 squared. This is the so Pythagorean theorem. Okay, and right, so Pythagorean. Okay, and so this is just kind of a generalization of the notion of length. The higher dimensions, the same sort of Pythagorean theorem. It just generalizes to more and more vectors. Think of now, I can think of this vector coming slightly out of the plane. Okay, right? So think of it as sticking a little bit out of the plane. Now I can decompose it into V1, V2 I see here, and maybe V3 is kind of sticking out into you, right? Hopefully not too far. I don't want you to lose an eye. And then to measure the length, well, I just sum up the V1 length squared, the V2 length, and then that third length, which is coming out of the screen, right? And that's the length of the vector. It works the same way, and you can add more and more dimensions onto here. Okay. Okay, so you can also think of this as, so V1 times V1 plus V2 times V2 plus VD times VD, right? And we take the square root of these things, right? So the first two is just what I've shown here, the V1 and V2, but then you can keep adding more and more of these terms on if you're in higher dimensions, and this still gives you the distance. And in fact, this is just V, the inner product of V square root, right? If you remember what the inner product was, it's just the, I take all of the terms from the two vectors of the same length, I multiply each terms pairwise together, and I add them all up. Well, that's exactly what I'm doing here, but just with the vector itself, right? So again, this inner product is showing up here in the definition of this norm. If I were to go back here, right, and I were to pick u and v to be the same vector, right? So u is a unit vector, say v was also 1. Well, then the length of it is the projection onto u is going to give me back the same vector. So I'm going to get back the length of v. Okay. So this should be consistent with what is going on here. I don't, when I'm doing this with the vector by itself, there's, I can avoid, I mentioned last time I can avoid u being a unit vector if I divide through by the length of u in this calculation. And so that's why you don't get a square in this case, because I've kind of factored that out. But just want to show you that that is consistent there. Sure. So, okay. Okay, now v can have any length here, right? I'm not restricting it to V1. If I want to make, I say, if the length of V is equal to 1, again, this is this special case I needed before, then I say V is going to be a unit vector. Okay, where unit is this term, unit refers to 1, right? The length of it here is 1. Okay, and if I want to turn V into a unit vector, I can just divide every coefficient by its length, right? So if I want to normalize, so often you say to normalize V, then I would go, let me, just so my V doesn't look too much like a U. Okay, so sometimes I say V bar, and this enforces that the norm of V bar is equal to 1. I do this by setting, so V bar is equal to V1 divided by the norm of V, V2 divided by the norm of V, VD divided by the norm of V. Okay, so what happens now if I square each of these terms and I add them up and then I take the square root, right? What's going to happen here is I'm taking a sum over I1 to D. I'm going to get V1 squared, VI squared divided by the norm of V squared. This can factor out of this sum. Right? So this term at the bottom can factor out the sum, right? And then if I take a square root, right, this norm of V factors out of the square root, and I'm going to get the two parts here, and this part is exactly equal to the norm of V, and this part here after the square root is going to be also the norm of V, so this has to equal to 1. Okay, so I can turn it into a unit vector by dividing every coordinate by the length. Okay. Okay, so this is an example of a norm. If I say just the norm of a vector, this is what I'm going to mean. However, this is actually a special case of a norm called the 2 norm. Okay, so not, okay, so if I say a norm, I don't always write this 2 here, but there's implicitly a 2. Okay, and in general, I can talk about a P norm of a vector, and that will be for a vector. I'll write a P down here. Okay, and this is for any P at least 1 and up to, but not including infinity. Infinity will be a special case we'll deal with here. Okay, and this is defined as the sum I equals 1 to D of the absolute value of VI to the power P, and there's all this to the pth root. Okay, right, so if I replace P with 2 here, right, then I get back what we had before. The 1 over P, the pth root is the square root, right? So this 1 over P is a 1/2, that's the square root, right? To the pth power, that's the square power. I have these absolute values in here. I didn't need to write those when P was 2, because when I square something, it's always going to be positive. So I didn't need to write those. So typically you skip writing those things there. So those absolute values don't affect the answer here. But in general, you do need the absolute values on the coordinates for the other values of P, other than even integer P's. There, it takes care of itself. Like if I put a P equals 4, right, that's also going to be fine. I don't need the absolute values here. Okay. If I put the P there, sometimes to be totally clear, I'll write this with the subscript 2 here for a vector. Okay. But if you don't see the subscript, you should assume that it's going to be a 2 when it's a vector of a norm. This is a very special. The 2 norm is a very special norm, but these all have nice properties. The 2 norm is the one that measures the straight line distance. Okay. There are other norms you can think about. Kind of the most common one otherwise is the L1 norm. And this one's also a nice one. Right, let's just write this out. The sum of the D terms, VI, absolute value, well now to the power P, that's to the power 1. So I can just skip that. Oh, and the Pth root, well that also disappears. Oh, so I'm done. Okay, so this is the definition of the L1 norm. I don't need to wrap it in a P. This one is also pretty nice. It's just the sum of the absolute values of the coordinates. Okay? And let me write out one other common one, and then we'll just look at some simple examples to make it clear. The L in the P equals infinity norm, what's called the L infinity norm. Remember, this was not defined for P equals to infinity, although this is kind of the case if I took P to the limit, right? What would infinity be? Now, it doesn't make sense because, well, I can't divide by infinity in the 1 over infinity, and that kind of cancels with the other P, so it's okay here, but what's happening with this L infinity norm? What happens if I take this to P to infinity? I'm going to sum up all the terms, take them to a really, really big power, but then take them to the root of that power, right? Let's say I put P is to 100, right? I'm going to take all the terms to the 100th power, but then take them to the 100th root. So kind of the coefficients cancel, so that's good, right? It's in meters to the power 100, but then the 100th root of that, so it's back to meters again, right? So the units aren't affected. But when I take it to the power 100, it really blows it up, and it makes some terms which are slightly bigger than other ones, way bigger than those other ones. And that kind of dominates. And so this is actually going to be the max over I1 to D of the absolute values here. Okay, so the L infinity is just the maximum term. The term that gets blown up the biggest, and then the other terms which are smaller than it actually don't matter anymore. And then I take the 1 over infinity its root, right? And so it gets back to the same units, and only the biggest one survived. Okay, so this L infinity is useful here. Okay, so let's go through simple example. Let's say V equals -1, 2, 7, and 5, right? Okay. So, okay, let's start with the 1 norm. This one's pretty easy. The 1 norm is going to be 1. This is the absolute value of -1, right? The absolute value of -1, and I'll skip this for the absolute value for the other terms, +2, +7, +5. Okay, so this should be 15. Okay, this is not equals to 13. Okay, a common mistake that people will make is they will forget to take the absolute value here, and they'll subtract this one. You get like a negative length sometimes, right? If the 7 had been negative instead of positive, it was a -7. You can't get a length. This is measuring some form of length still, different from the straight line distance, but some form of length. If I had a -7 there, then I would get a negative value for the length, and that would not make sense, right? I have to take absolute values here before I add these up, okay? Okay, let's do the, so this is the L1 norm of V. Okay, if I take the infinity norm, this is just the max of the absolute value. So this one is also pretty easy. It's just 7, right? That's the one that's the biggest, right? And if it was if I had a -7 instead of a 7 there, right, it would still need to be, it would still have to be 7. It's the absolute value of that term there. That's the biggest. Okay. If I do the 2 norm, this one I probably would want to calculate with Python, probably because I'm lazy, but let's try and do it. 1 squared plus 2 squared plus 7 squared plus 5 squared. This is 1 plus 4 plus 49 plus 25. And this should be equal to, what's the square root of each of these things? Square root of 79, right? And this is equal to about 8.88, I think. Okay. Okay, so that one you can calculate as well. This one is the one you use most often, and that's the one that, you know, I'm probably not going to ask you to take a square root of 79 on a quiz or something, but this is the mechanics of how you would do this. Okay. Great. Okay, let's draw a useful picture here. This is a picture I like to draw a lot. Think of an origin here, and now I'm going to draw. I want to draw the set of all vectors. Set of all vectors with the 2 norm equals to 1, right? All the vectors on this 2-dimensional plane with the length of 1, 2 norm length of 1, right? Right, so I said it's the length of the vector if I took a piece of string and I put the string on there and the string was length 1, that had to be the length of the vector. So what I can do is I can bolt one end of the string here and I can kind of swing it around like this, right? And that's going to give me a nice circle here, right? So I'll say this is the vector value 0, 1. Out here is 1, 0, and this is 0, -1, and this is -1, 0. These are kind of key points. All these are vectors of length 1, right? These are, you can see these points are vectors of length 1, and then what fills in is the circle, right? This is a circle, okay? And if I wanted to draw the vectors of length 2, well, it's a circle with twice the radius and so forth. So let's fix the ones of length 1. Okay, now we'll say in red, let's do with the 1 norm. Instead of the 2 norm equals to 1, let's do with the 1 norm equal to 1. Okay, well, we'll start with saying, I'm going to tell you that these 4 points still have a 1 norm equal to 1, right? Remember, I added up the absolute value of the coordinates. So even though it's -1, this is a length of 1 still. It's 1 plus 0. All of these are 1 plus 0. Okay, so those 4 points are the same. Okay? Who can come up with another point that will have a 1 norm of equal to 1? Any other point? Yep. 1/2, 1/2. Yeah, so 1/2, 1/2. Let's say, let's tick marks here. This point right here. So that's coordinate. This is 1/2, 1/2. Okay. And so this is also going to be true, these 4 points. If I turned any of those 1/2s into a negative 1/2, I take the absolute value, right? Okay, so how do I fill in this so L1 circle? Yeah, back there, the diamond shape, right? So I draw them like this. These are all the points that have an L1 norm of equal to exactly 1 here, right? It's coming inside. They touch at the boundaries here, but otherwise they kind of come in here. Okay, cool. Okay, and now let's do one more exercise. The L infinity norm equals to 1. Okay, let's, again, I'll give you a hint. These 4 points all satisfy this because the maximum of any one of the coordinates is 1, right? What other points kind of are going to be on this L infinity circle? What are other interesting points? Oh, back there? That's right. Ah, so 1, 1. Great. Right, 1, 1. Okay, the maximum of those two values is 1. They're both 1. Okay, but and anything that has if the x value is 1, but the y value is less than that, that's also going to satisfy this, right? The y value is less than 1. Well, the maximum of the two is still 1. And I can also say the y value is at maximum 1, right? And then I can also draw it down here because I'm doing absolute values. So it's going to be symmetric across the origin. Okay, so this is the L infinity ball now. That's this square shape. Okay, and as you can define like a p equals 3 ball, and it's going to sit in between the p equals 2 and the p equals infinity ball. You can define a p equals 1/2 balls in here. You know, so these are notions of these circles, but they're different notions of distance, right? These are all things at a distance of 1 from the origin here. Okay, I want, if you want to kind of think about some cool stuff, think about what these look like in even higher dimensions. We won't need to use that in this course. That becomes important in like the machine learning and the data mine course, but I will leave that to those courses to really develop that. But that's a little bit fun to think about. I just want to give you a notion that these are different ways of measuring the length of a vector, and they're all kind of internally consistent if I can use that with each other. Okay, I can also I can also get a distance from a norm. I can call an LP distance between two vectors, let's say V and P, right? The idea is I can do V minus P here. So I can get some distance in between vectors, right? So I could say, what's going on here? I've got 2 vectors. Let's call this one, this is V. I've got another vector here, call this one P. And I want to measure the distance in between them. How different are these vectors? Well, let's do like the L2 norm. This is easier to think about. You could use one of the other norms, but let's just do the L2 norm. Well, the distance between them, I should think of now them as points. Okay, and the distance between the points is just this length here. Okay? So why does it make sense to write it in this way? Well, if I subtract P from V, remember I did subtraction by taking, I can add vectors by just stringing them together. So I'm going to take this guy and I'm going to go back the other direction. Instead of subtraction, this is minus P, this minus P vector from V. And what should be left here, this should now be V minus P, is this vector here. What's nice about this is now a vector from the origin, this V minus P vector, and so I can measure its length as a norm, right? The norm measures the length from the origin of this vector, and that length from the origin is the same as the length in between the two here. And this is true if I measure length with the L1 norm or the L infinity norm or the L2 norm. But with the L2 norm, it's the straight line distance. Okay, and so that is preserved here. And so most intuitive here with the 2 norm. Okay, questions. Great. Okay. Okay, great. So I can take a distance here. We won't talk too much about distances, although they are important. We'll always, in this course, we'll always use the L2 distance, right? The distance defined, the Euclidean straight line distance. But in, say, in the data mining course, if you take that, we'll spend like several lectures thinking about different distances and how that affects things. But we'll keep it simple within this course. Okay, great. Okay, let's speed it up a little bit. Okay, so we can also take a norm of a matrix. Okay, so let's say I've got a matrix A and R n cross D, and so I write this as the norm. And now there are two basic types of norms of matrices. There are more than two, but I'm going to focus on the two most common ones, and they're kind of both extensions of the LP norm of the 2 norm. Okay, but I write them with different subscripts because they're different extensions of it. The most simplest one to understand is you put an F as a subscript. This is called the Frobenius norm. The Frobenius norm. Okay, and this is kind of like taking the matrix and treating it like it's just a long vector that was wrapped around. So what I do is I take a sum over all of the rows, and I take a sum over all of the columns of Aij. So this is all of the entries over the entire matrix. I square each of them before I add them up, and I take the square root. Okay, so this is the Frobenius norm. If I write A as a bunch of these matrices of these vectors stacked together, then I can write this as also, this is sometimes useful to think about, right? If I can put another little L2 norm inside of here, squared, because the squared L2 norm is actually just is the same thing that's going on here for fixing I. When I fix I, right, then, right, it's the same thing here. That's the squared norm of the ith row. Okay. All right. So this yeah. Question. Yes. Great. Thank you. Good. Okay. Down to and. Great. Right. So this is the Frobenius norm. This kind of measures, I'd like to think of it as kind of like the total mass of everything captured and the total, all the variation, all the kind of the difference from an all zeros vector way of measuring that. The second one is called the spectral norm. This is sometimes is called like an operator norm. And this is the one that gets the 2. This is, if I use a 2 subscript, you could think of this one, you could have done this with like an L1, and there are versions of it. You want to get it so it's kind of consistent in certain ways. But this is kind of like an L2 norm already, but it's over all the elements. But this one gets an F in front here. This spectral norm is what gets the 2. Yeah.
The second expression, I think, the summation.
Up to N. Great. Thank you. Good. Good. You guys are paying attention, which is good. All right. So I was supposed to claim you actually meant to do that to see if you were paying attention. So, okay. 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 So this one is a little bit trickier to understand. This involves a max. Okay. I mean, there are other ways to define this, but this is, I think, the most intuitive way to define with the machinery we have now, with the norm not equal to 0. Okay, so I'm going to take a set of vectors, any vector in RD that's not the 0 vector. Okay, any vector in RD, and I'm going to do AX. Okay, so I'm multiplying x times a, right? And then I'm taking the norm. X times a, or a times x in this order, is going to give me a vector, right? Multiply it by length d vector, then it's going to output an n-dimensional vector. And it's a vector, so I can take a spectral, a 2 norm again. Implicitly, this is a 2 norm here. Okay, and then I divide by the length of the vector. So I can take out the scale of the vector. I could have assumed that x was going to be a unit vector over all unit vectors here. But I'm saying the maximum I can get by multiplying by any vector here, right? I could also say the max over u in RD such that the norm of u is equal to 1. And then I can just write this as a of u. Because then the length is 1, then this part cancels out. So I'm multiplying by any unit vector, and I say, how big can that possibly be? Called the spectral norm. We'll talk about eigen decompositions later in class. And this will make sense, or the singular value decomposition. And that'll be a key thing we'll spend several lectures on. And how to think about it, and this will make sense in this context. The spectral refers to this eigen decomposition property and the singular value decomposition property here. Okay, it's also true, you can also write this as the max over y in Rn, where y not equal to 0, and then I can write this as the left multiplying by this. Okay, so I can left multiply. It's going to give the same answer if I do it this way as well. So it's not so important that I right multiply versus left multiply. It's going to be the same answer, but now this is n-dimensional vector to get the dimensions to work here. Okay, and there might need to be, you might need to think of one of these transposed, but I tend to kind of implicitly, it's the dimension it's the row or column dimension which works in the multiplication. In fact, Python does the same thing. We'll see that in a few minutes, that you can pass in any orientation and Python will just make it work if you use like the dot product symbol. Okay. Okay, great. So these are lengths. This tells you essentially, now length may not be the appropriate term here. Just think of it as like a scale factor. How big is the matrix? If a matrix tends to have bigger values in it, the entries are bigger, well then the Frobenius and the spectral norms will also be bigger, right? If they're smaller, they become smaller. Putting a negation in there, well, that turns out to kind of be tricky because for the Frobenius norm, then negations don't matter so much, right? Because everything gets squared before I add them up. But in here, I'm multiplying by a vector, and sometimes things might cancel out a little bit in that process. So this one's a little trickier to think about. Okay, and I'll delay an example until we go through just in Python. Yeah, this Frobenius norm is always bigger equal than this one. So the other property we have is the Frobenius norm of a matrix is always greater or equal than the spectral norm. This is, and when we talk about singular value decomposition, we'll figure out a different way to describe these, and then it will become very clear that this is why this is the case. Okay, but for now, you can just worry about the definition. These will be our notions of scale of how big is a matrix. Okay. Okay, great. Before we get to Python, I want to talk about another really important concept, linear independence. Okay. Okay, so this is kind of a, all right, so let's think I've got K vectors now, V1, V2, up to Vk. And these are all in Rd. So these are d-dimensional vectors. And I also have K scalars, alpha 1, alpha 2, up to alpha k. Remember, I was going to use Greek letters for scalar quantities. These are not vectors, these are just a single value. Okay. And so the key thing is we're going to think about this vector z, which I'm going to write as follows: alpha j times vj. Okay. I'm going to do this operation. I'm going to take v or k of these vectors and multiply each vector by a scalar. And what does the scalar do? It scales it and makes it shorter or longer based on how big that alpha value is. And then I'm going to add them up. And I'm going to get a new quantity v. What is this quantity? Is this a matrix? Is this a vector, a scalar? What is this?
Wouldn't that be a vector?
Yep, yeah, that's right. It's a vector, right? In fact, it's in the same space Rd is before as these other vectors, right? Because if I add two vectors, it's an element-wise addition. If I have a scalar multiplied by a vector, I scale all the quantities, all the coordinates by that alpha term, right? So if alpha is 2, then I'm taking all these quantities, all the coordinates, I'm multiplying them by 2, right? That's what's going on here. So the alpha times b, right, that gives me back another vector, and then I'm adding vectors together. Okay. Okay, what is kind of important? Why did I use? Okay, the book uses X instead of V's here, but that's just fine for now. Okay, so what's interesting to think about is if I fix, now let's fix these vectors, and I say I'm allowed any of the scalars, right? Then I'm thinking, what z's can I possibly get? What are the z's I can get here if I fix the vectors, but I say I can scale them in any way I want? There's kind of a preview here. If I have a single vector v1, then the set of all of the vectors I can get by scaling it are kind of all the values along this line here, right? I can scale it to be larger, right? I can make it larger. I can make it smaller. I can negate it and go backwards across the origin. Okay? So that's if I have a single vector, but if I have multiple vectors, and we'll think of in this case, this is interesting typically for now when k is less than d, right? So d is now a high dimensional space, right? We're thinking in high dimensions. and K is something that's less than that. Think D is 10 dimensions. I'm in 10-dimensional space. And then K is 5 or 6. Okay, what is going on here? Okay, we'll think about this in low dimensions, and then we'll scan this up. Okay, so this case, when I say if I fix the K vectors V and I look at any scalars, then any Z that can be written with some alpha up to alpha K with some set of these scalar values. Any Z that can be written with some of these is called linear dependent on the set V1 up to Vk. Okay, so the Z's that I can write in this way are the ones which are called linearly dependent on those vectors. Okay, and if Z prime cannot be written this way, then it is linearly independent. Okay, so if it cannot be written in this way, then this is what's called a vector which is linearly independent on these guys, on these vectors, V1 through Vk. Okay, so if I think about this, if I only have one vector V1, then everything on that thin red line are the things which are linearly dependent on it. And then something off of here, this would be a Z prime. I cannot write it with a single scalar of V1, this Z prime term here. Okay, I cannot write it in this way. So it's going to be linearly independent of V1. Okay. This set, right, one more thing in here. This set, actually, let's just do this on the next page. So I can write this again. I can say the set, let's write the set of vectors Z such that Z equals the sum over K of alpha I Vi for any alpha I in R, right? These alpha I's are in R. Okay, this is called the span of this vectors V. Okay, so the span of the vectors V. So for just this one vector, it's this red line, but in higher dimensions, it gives me this kind of this space of vectors that I can write, the set of vectors. It's as you can imagine. Okay, let's try and imagine this. When I have one vector, it's kind of everything along the line. So it's a continuous space, right? If a vector nearby it is, it's going to be a space that is going to be continually varying. It's not going to be, you can think of a set as like a discrete set of quantities. This is not going to be a discrete set of points. It's going to be a continuous continuum of points, a smoothly varying thing. And it's going to be kind of what's called a linear kind of subset of RD. Okay, so it's going to be an extension of a line. If I have two vectors, it's going to give me a plane, a two-dimensional plane. So in 3 dimensions, we can think about this. We live in 3-dimensional space, and there's some plane, right? This sheet here, if I fix it, I'm seeing part of it, but it expands off to infinity in every direction, just like the line did, but now in 2 dimensions, it expands off to infinity. And they aren't necessarily just like, the board is an example too. The screen you're looking at is a 2-dimensional plane living in 3D, but I don't have to restrict it to be the original coordinates. anymore, okay? So this is a little bit more general way of thinking about kind of a subspace in higher dimensions here, okay? If the span of a set V, if this is equal to RD, so I can say that if it is the whole space, for instance, if I have D or more vectors, then I might likely get this property. Then we say V is a basis for RD. Okay, so I said this was going to be the basis of what we do a lot later in the semester. That's what why I was laughing to myself earlier in the lecture. So if I think if I can get Z, if I can have Z represent any point in RD, right, then that set V of vectors that I have is going to be a pretty special set. It's a nice set in that I can use it to get to any other point I want to in space. So that means it's a basis for all of RD. It allows me to get the same way a coordinate system allowed me to represent every point, but this is a different way of doing it. A different way I can represent every point in this sort of form, this linear form. Okay. Okay, let's do a little example here. Okay, let's look at two vectors called V1, 1, 3, 4, and V2, 2, 4, 1. Okay, so we are going to be thinking in high dimensions now. These could be higher dimensional vectors, and we're going to just work through everything algebraically. We don't have to actually place them in some weird high dimensional space we have to think about. We can just use the math of linear algebra to kind of organize our thoughts and our algorithms about these high dimensional data. Okay, so let's go through an example. And then we have two other vectors, right? So these are both vectors in R3. I just kept the example small because large examples just kind of, other stuff gets in the way. Okay, -3, -5, 2. Hopefully this is a good example. 3, 7, 1. Okay. So let's see which of the vectors Z1 or Z2 are linearly dependent or independent on X. Let's see if is Z1 linearly dependent or independent of V1 and V2. So can I write Z1 equals alpha 1 times V1 plus alpha 2 V2? Is there a way to do this? Yeah, okay. So how do you think I can do this? Okay, let's try what alpha.
So alpha 2 would be negative.
And alpha 1 should be 1. Okay, let's try this out. This is going to be 1, 3, 4 plus -2 times 2, 4, 1. Okay, this is going to be 1, 3, 4 plus -4 -8 -2. This is going to be -3 -5 2. Oh, great. That works. Okay, good. So I get back -3 -5, and this is exactly Z1. Great. So Z1 is linearly dependent on V1 and V2. So this is linearly dependent. Good. Now let's think about Z2. Can I do this the same way? Alpha 1 prime V1, alpha 2 prime V2. Can I choose alpha 1 prime and alpha 2 prime in such a way that I get Z2?
No.
No. Okay. This is a little bit trickier to see, but yeah, so why can't I do this?
Consider what happens if you just pick one for both the.
Okay,
alpha one
let's
and alpha two.
let's try that. I'm gonna get, so 1 plus 2, I'm gonna get, let's see, 3, then 7. That's looking pretty good so far. Oh, wait, 5. This 5 is not the right thing here. So I matched the first two, right? I matched the first two. So I could have made, maybe I could try making alpha 1 smaller and alpha 2 bigger, and they could maybe cancel out. But if I trade off, the last one is always going to be wrong. Okay, so I can't set alpha 1 and alpha 2 anyway to try and get all 3 coordinates to match at the same time. Okay. Okay, great. So these are kind of not, so Z2 is going to be, so this one is going to be linearly independent. Okay, and this is a little bit trickier to do. I'm not going to kind of give you an algorithm to kind of fully do this, but you can kind of, try and line them up. And usually the examples I'll ask you to think about are going to be small enough that you can kind of figure it out in a similar way. Okay. Okay, so one more piece of terminology, and then let me draw some pictures, and we'll go to Python. Okay, so let's say a set of vectors x1 up to xn. Okay, and these are going to be, and I can call these vectors linearly independent. Okay, so this is now, I'm not measuring a set V against another vector. I'm saying these vectors themselves are linearly independent if the following property holds. That's for each, or no, actually, for any xi, okay, there's no way to kind of choose scalars alpha 1 up to alpha I minus 1, alpha I plus 1 up to alpha n, such that xi is equal to sum equals I equals 1 up to n, except I not, j, except j not equal to I of alpha I xi, right? So I can't take out one of the vectors. There's at least one vector I can't take out, so that I can recreate it with the other ones. Actually, this is for each. This is true for, yeah, I can't take out, for each of the vectors, I can't take it out and recreate it with the other ones. Okay? So if these are, if I could take one out, right, and then recreate it with the other ones, that means I kind of don't need it to represent the same basis. The span, right, remember the span is the set of all vectors I can represent with these. And so if this was not true and I could take one of these out, then I could take out that vector and the span of the data would not change. I would not get kind of a different subset of vectors I can represent. So when they're linearly independent, that means they're each kind of important for defining the span, right? The space of vectors I can reach. Because if I can recreate one of them, well, then I can factor it out by choosing the alphas a little bit more carefully, setting that alpha equals to 0, right, in the thing. So it, okay, so this is when a set of vectors is linearly independent. All right, and let's draw one picture of an example here. Let's draw A is going to be equal to 1.50, 2, 0.5, and this is a matrix 1, 1, right? Okay, so this is going to be 3 vectors here, and I can draw each of them. 1.50, so let's is, okay, so the x coordinate 1.5, yeah. This is going to be 1.50. Okay, the blue one is going to be 2, then 0.5. I want to switch this one around. Okay, hold on. 0, 1.5. Okay. Okay, let's do, so 0, 1.5, this would be 0, 1.5. Then 2, 0.5 might be here, 2, comma, 0.5. And this will be a useful example to think about. And then 1, 1 might be somewhere in here. Okay, and so I can think of these as individual vectors. Okay, but what is interesting is the way I've chosen these is so that there's a line which goes through these all. I can draw all 3 of these on a line that goes through these 3 vectors. Okay, so so what this means is I can represent, I can think of representing this one by just interpolating in between these other 2. But I'm interpolating and I'm changing the weights of these 2 vectors. So I don't really need this. This one is not adding into the span here. Okay. Now the span is different. The span also includes the origin, right? I always get to use the 0, 0 vector. In this case, there are some cases when you're dealing with like probabilities, you kind of enforce that you can't use 0, but okay, we're always using 0, 0 also, so I also get everything else here, but I'm not getting stuff out of the plane. I'm only in 2 dimensions. But you can think of this line that kind of goes through these, then I don't, this is a way to draw a 2-dimensional picture. We can kind of see that there's this dependence on these, but we write one as the others here. Okay. Okay, so in general, we'll be talking about there's some lower dimensional subspace that goes through all the data that could represent in high dimensions. And we'll talk about how to calculate this, how to represent it in a cleaner way, and how to work with it for dimensionality reduction and regression. Okay, so I didn't, let me quickly jump to this collab thing. Again, this is linked off the web page right here. And I can get to this collab file. And let me just for 5 minutes just go through this. And we can go do this again on Thursday. But I wanted to get through all of that before your quiz on Thursday. Okay. This will be useful in the homework. So we're going to use a LaTeX, a Python package called NumPy. NumPy is kind of the package that allows you to work with vectors pretty easily. And then there's also a linear algebra package that'll have some of the operations in it, right, within this and all. So I import NumPy as NP. That means when I call a command from NumPy, I don't have to write NumPy dot something. I can do NP dot something. I'll do this here, NP dot array. I've shortened that. And I've also imported the linear algebra package as just LA. Okay. And then the print command prints it out. I created an array by this np array command. It tells me this V is now an array of length 4 in this case, and I can print it out. Okay. I can index into it. Says the second index is 7. This means it starts counting at 0, right? 0, 1, 2. So the second one, the index 2 is 7. Okay, I can also create a a matrix, right? I do that by kind of nesting arrays, right? I have two open parens, open of the square brackets, right? And then I write the first array, comma, the second array. That's the two rows in the matrix A, and I printed it out here. You can index into it now by 2, 1, and 2. So that is, I go to row 0, row 1, and then I go over 0, 1, 2, I get a 7. Right, so I can index into it. And I can also print out parts of it using these colons. Colons means print out all the rows. I got both the rows, but all the columns starting from the first column. So I removed the 0 column and I printed out the rows. I can also ending at a certain column on the other side there, right? This kind of like MATLAB if you've used MATLAB before. All right, this is another matrix. So I can create another array U and I can add them. You add them by just doing a plus, right? So this is pretty easy. I can just write it like a plus and it automatically adds together the two arrays. It internally is doing the for loop and all that for me. This is element-wise multiplying. If I do a star, which is sometimes a product symbol, I don't get a dot product or something. Here, I multiply the entries, element-wise entries together. Okay, so that is not the dot product. If I want to do the dot product, there are many ways to do the dot product. Here are 3 of them. The dot product is so important, it shows up in many different forms. Probably the easiest one is V at U, right? That gives me a dot product, especially I can do V dot of U and do it. I can do inner instead of here. So it's a function built into that things, or I can do NP dot and it takes in 2 arguments. Sometimes you string together a few of these and the nesting of the parentheses is uncomfortable unless you're a functional programming person. Where the ats, you can just chain them together. So that's often preferred. You can also, yeah, I've got another matrix here. Let's see, so now matrix multiplication is also basically, they think of it as an extension of the dot product. So I can also just apply an X symbol here, and that does matrix multiplication. I don't put them next to each other. Unfortunately, that's a little bit harder for an interpreter to figure out what you want. But with the @ symbol, that works pretty easily. And I can do matrix vector. And so the dot also does the same thing. The matrix vector multiplication does this. An interesting thing to see is that, like I mentioned, it doesn't pay attention to what way the vector is oriented. It says if you're multiplying, there's only one way that that you can orient it, so this is a legal operation. So even though I did X and X, this is a transpose, it gives the same result. It doesn't complain. Okay, even though that technically the dimensions aren't the right way, it says you must mean this, for better or worse. So keep that in mind. Okay, norms. For the norms, it's I need the linear algebra package part, and so I have LA norm. If I don't say what type of norm it is, what the p-value is, it assumes it's a 2 norm, just like we will in class. But if I write the 2 norm, I get the same thing. Again, this is the same example we did in class. The 1 norm, you put a 1 for the Frobenius norm, or the infinity norm. You use the symbol for infinity in NumPy, np-inf, in there. Gives you the infinity norm, which is the max norm. Okay, I can do matrix norms, right? And again, the fro or the 2, and it gives me slightly different answers. The Frobenius norm is bigger here. Turns out it's not much bigger in this case, and we'll understand that why a bit later in class. Yeah, transpose the dot t. Again, perhaps confusingly, it always prints a vector as a row. 3, 4 here. It always printed the row vector. Okay, so even though I transposed it, says you want to print this as a row because printing column vectors is very tedious. It takes a lot of space, so it always prints it as a row. Okay, and then the rank we will talk about, and the inverse we'll talk about in the next lecture, maybe I can review this and take any questions next lecture on this NumPy stuff. Okay, great. Don't forget your quiz is on Thursday, so do your cheat sheet and get that ready to turn in. All right.